of quantum resource testing via blurring.
All right, thank you very much for attending. And okay, so I think you heard enough about the generalized quantum science lemma. Now you're gonna hear a little more. But for this reason, I want to jump right in and somehow tell you more about the technique and what else you can do with this technique that I call blurring. Okay, so this is based on these two works. The second one with Mario Berta and Bartosz Regia, also here. Right. Okay, so let's start from the setting. Let's quickly review the setting, but Hayata already explained it very well. Okay, so there are these two subfields, quantum hypothesis testing and quantum resource manipulation, and there's this fundamental technique, fundamental result by Brunel and Plenio that connects the two, which is called this generalized quantum science lemma. Okay, this is something they proposed a proof of, and later, okay, Hayata and Masahito proved, and also I proved in this first of these two papers. And I also want to highlight a second connection, which arises very naturally in the same framework, and it's encapsulated by this generalized quantum Sanov theorem, which is somehow a complementary version of the generalized science lemma. Okay, I'm not actually going to discuss very much the quantum resource manipulation side of things, and we're just going to focus on quantum hypothesis testing, because the connection, again, has been explained very clearly. And I want to highlight that both of these results can be derived with a technique, the same technique that I call blurring. Okay, so we'll see the applications of this technique to both of these results, and it's kind of quite different how it's applied. Right. Okay, so let's start from the very beginning. So let's say this task of entanglement testing. I'm going to focus on entanglement, but you can apply this to many other quantum resources. So the task is that you bought a device with a big red button, and it's promised to you that whenever you press the button, it outputs an entangled state rho AB. Entangled means just non-separable. And what you, however, suspect is that I have to press like this. Okay. What you suspect is that the device is kind of maliciously engineered, so when you press the button, it spits out a separable state even after n uses. And how many times do you need to press the button to decide whether the device is functioning correctly or faulty? Okay, so after n uses, you have this kind of situation. You have an unknown quantum state of many Alices and many Bobs. They don't know what the global state is. It could be either rho tensor n, and rho is something that you know, or it could be a global separable state between all the Alices on one side and all the Bobs on the other. And how do you decide? Well, you make a measurement, and like in every time in hypothesis testing, when you make a measurement, there are two types of error. Type 1 error, when the state was rho tensor n, but you guess separable, and type 2, when the state was separable, but you guess rho tensor n. And these two errors, they're not necessarily equally consequential, so we want to treat them differently. So and this gives rise to two different settings, the Stein setting and the Sanov setting. In the Stein setting, you want you have this constraint on the probability of type 1 error, which is at most epsilon, and you want to minimize the probability of type 2 error. And this will decay exponentially fast, and you want to calculate the coefficient. It's just a bit erratic. Okay. You want to calculate the optimal coefficient, this gamma, which is called the Stein exponent of entanglement testing. Okay, so the rate of decay of the probability of type 2 error. And in the Sanov setting, you want to do the opposite. You have a bound on the probability of type 2 error, and you want to minimize the type 1 error probability. Okay, and you want to calculate again the optimal coefficient there, which is going to be given by another number, delta, that I call the Sanov exponent. Okay, of course, you could also say this is just a Stein exponent if you flip the two hypotheses. Yes, true. But it's kind of helpful to keep the terminology distinct. Also because the two hypotheses are very different. One is composite. It can be an arbitrarily non-IID state, very correlated, even entangled across the different Alices and the Bobs. And the other one is just IID for now. And so this is the reason why the one setting, one result does not imply the other. And but both exponents are important because they quantify the ultimate performance of entanglement testing. So we want to really calculate them. And how do we do this? Okay, so the key quantity here is one of the key quantities is the relative entropy of entanglement. Okay, so well, let's start from the relative entropy. The relative entropy, you all know, it's the Stein exponent between any two fixed quantum states, right? So if you are in the IID scenario, Hiai and Petz showed that this is the correct Stein exponent. Okay, so then you could say, okay, I try to, since we are discriminating the state against all separable states, I could try to look for the worst case scenario over separable states in the second argument and try to minimize the relative entropy. And that's going to be my worst case Stein exponent. And of course, since we are doing quantum theory, unfortunately, we have to regularize this quantity to get the regularized relative entropy of entanglement, okay, which is just given by, you take n copies of the state and then an arbitrary separable states over n Alice systems and n Bob systems. And in general, you need the regularization, okay? So this quantity is non-additive, it's well known, so you need the regularization, which is not necessarily easy to calculate. In fact, it's very difficult to calculate in general. And in the Sanoff setting, you can just do the opposite. Since the separable states now are in the first argument, you can try to minimize over separable states in the first argument. And in this way, you get a reversed version of the relative entropy of entanglement. And now you could also ask yourself, okay, what happens if I regularize this one? But this one is actually additive. Very surprising, but it's actually quite simple to show. And really follows just from subadditivity of entropy. Nothing difficult, but it's quite surprising that for this reverse version, you don't need any regularization. So this means this is given by a single letter formula. You can actually calculate this, or you have some hope of calculating it. And this additivity we show in this second paper. Right, so now the main results of this talk are the calculation of both of these exponents, okay? So you have the generalized quantum Stein's lemma on one side, which tells you, okay, the Stein exponent is the regularized relative entropy of entanglement, and you have the generalized quantum Sanoff theorem on the other side, which tells you the Sanoff exponent is the reverse relative entropy of entanglement. Okay, nice. In fact, what I prove in the paper is a slightly stronger version of the generalized quantum Stein's lemma. So on the one hand, I use indeed all of the 5 Brandau-Planio axioms, as Hayata said, but the bonus that you get in this way is that you can prove a stronger version that applies also when the source is non-IID. So it's almost IID. And this is the first, it's one of the first examples where we can solve this kind of problems for when both hypotheses are composite. Okay, so it's kind of non-trivial extension. So by almost IID, I mean that, for example, one way to think about it is that it's not exactly accurate, but let's say instead of row tensor n, you allow yourself to corrupt a few sides. So a fixed number of sides, let's say k, and this number has to be fixed as n goes to infinity, but you allow for this corruption. This can happen everywhere or anywhere. And you can still prove the Stein's lemma. So you can still do, even if the source is corrupted, you can still do entanglement testing at this rate. Okay, so the other thing I want to emphasize is that this generalized quantum Sanoff theorem gives an operational interpretation to this reverse relative entropy of entanglement, which is a single letter entanglement measure with an asymptotic operational interpretation. And this is kind of a very unique among entanglement measures. Usually when you have an operational interpretation, it's very difficult to calculate because it's regularized. But in this case, for some miracle of the relative entropy, it's not. Okay, and okay, so all of what I'm saying applies to other quantum resources, for example, quantum magic. Okay, in fact, I mean, like essentially any quantum resource you want to look at, you can apply this to. Right, so the proof structure is like this. So you first have, so this blurring technique, the first instantiation is this classical blurring lemma, and this gives you immediately the generalized quantum Sanoff theorem. So if you want to prove the generalized quantum Stein's lemma, it's a bit more difficult. You need a bosonic lifting technique to kind of, to give a quantum version of this blurring lemma, and with that you can prove the Stein's lemma. Okay. Right. So the first thing I want to explain is to you is how the blurring technique can be applied in the Stein setting. Okay. And let's do only the classical case for now because it's much easier to understand. Right. Okay, so the two expressions we need to calculate are like this. The Stein exponent is given by this horrible expression in terms of the hypothesis testing relative entropy. It quantifies the rate of decay of the type 2 error exponent. And the Sanoff exponent is given by this other horrible expression in which the minimization, instead of being the second argument, is on the first argument. Okay, but they are very similar. Okay, so and the main insight, well, the first main insight is that like this, the problem is a bit too difficult. So now we, instead of the hypothesis testing relative entropy, we go to another one-shot relative entropy called the smoothed max relative entropy, which has just been introduced by, well, for example, Nilanjana, and then many people have worked on that, including Masahito Hayashi and Marco Tamamicho. So it's given by this expression. So you see, you are trying to, well, first of all, you're given two states, and you smooth over the first state in the trace norm, and you try to dominate this smoothed version of the first state with the second state, with a multiple of the second state, in the semi-definite order. Okay, so the kind of the miracle here is that the hypothesis testing relative entropy is entirely equivalent to this smoothed max relative entropy if you are willing to change the epsilon. So you see, you can give both lower bound and upper bounds on dH, given this d max, in terms of this d max, but you, instead of epsilon, you end up with 1 minus epsilon, or square root of 1 minus epsilon. Okay, so somehow you flip between epsilon going to 0 and epsilon going to 1. Okay, so this is kind of the tricky part. So this relation is a tight version of a relation proved by Hayashi and Tamamicho that we proved in this paper, recent one, in January, with Nilanjana and Bartosz. Okay, so the shorthand notation, first of all, will be that when I write a set in the second argument, I mean always a minimization over states in the set of the corresponding divergence. In this case, the smoothed max relative entropy. Okay, so now you have all these equivalent expressions. Instead of dH, now I put d max, and the price I have to pay for that is that instead of the limit epsilon going to 0, now I have epsilon going to 1. Okay, we don't seem to have gained much. But what we will actually prove is that the limit in epsilon doesn't do anything. So in fact, what you can prove is that both of these quantities, the limit exists for any fixed epsilon, and it's given by the regularized relative entropy, as it should in the Stein case, and the reversed relative entropy of entanglement in the Sarnoff case. Okay, so somehow the limit in epsilon doesn't do anything, which is usually the case. But in this case, I mean, it's kind of difficult to prove, but it's physically expected because the limit in epsilon should not. I mean, it's just why should the asymptotic behavior be affected by whether you fix epsilon to be 1% or 10%? It doesn't make any sense. So it should not depend on epsilon. And in fact, this is what happens. Okay, so kind of there's an easy statement that you can make is that if instead of the limit epsilon going to 1, you take the limit epsilon going to 0 of this d max quantity, in fact, you can prove that this is equal to the regularized relative entropy of entanglement, this minimization in the second argument. This is known, and it's not too difficult to prove. You just use the strong converse of the IID quantum Stein's lemma, which was known since Ogawa and Nagaoka, and you use asymptotic continuity of the relative entropy of entanglement for the converse. So this is kind of the known part. And now the difficult part is to show that, so you see that the smoothed max relative entropy is really a nightmare, but one thing we can say is that it's decreasing in epsilon, okay? Because you remember you try to minimize over a smoothed, over an epsilon trace norm ball. So then the more you enlarge epsilon, the bigger the ball is, so that the function must be decreasing. So what we want to prove, the non-trivial part is to prove a lower bound on this smoothed d max. Okay, so kind of informally, the statement we want to prove is that given any epsilon, which might be not small, like, I don't know, 0.7, you want to lower bound this quantity in terms of another d max, but now with very small eta. Somehow this is, and if you do this, then by this known result, this smoothed d max for very small eta is basically the regularized relative entropy of entanglement. Kind of this is the gist of the proof. The whole point is to prove this inequality. Okay, to relate d max with different epsilons, well, from epsilon to eta, from a large epsilon to a small parameter. Right. So, and kind of a key intuition by Brandao and Plenio, and I really can't stress enough how important this is for like thinking about the proof, is to abstract this even further, to move away from entanglement and to just list a number of axioms that you want to have in order for this result to be to hold. Okay, so let's say we move into the framework of quantum resource theories, you have a base Hilbert space H, and then for every n, you have a set of so-called easy-to-prepare states, which we call free states, which is just a set of density operators on n copies of the system. And we're going to assume a few things. For example, we're going to assume that, well, okay, every set is closed and convex, and the first level of the hierarchy contains a full rank state. This is very important. And then there is this other bunch of assumptions that, for example, the set is closed on the partial trace, it's closed on the tensor products, and permutations, okay? So the set of separable states obeys all of these axioms. The set of stabilizer states obeys all of these axioms. The set of PPT states obeys all of these axioms. So essentially, many of the, if not all of the quantum resource theories that we used to look at obey all of this. Okay. But now the advantage is that we can just take these axioms and just apply them to classical probability theory. Why not? You can say you have a finite alphabet, and then you have a set of free probability distributions over n copies of the alphabet, and you can impose the Bernoulli axioms. No problem. These are operational axioms, like discarding systems or discarding variables should, from a free state, should give you a free state. This kind of operational assumptions you can also apply to classical. And now what you have to prove is exactly the same thing, but now with classical probability distributions instead of quantum states, and I call now Fn the set of free states, free probability distributions, okay? So about the same thing to prove. Okay, so let's proceed by contradiction. So let's say this is not true. So this means that the Dmax epsilon is really affected by the epsilon. If you increase epsilon, it really goes down asymptotically. This is, by contradiction, this is what we should assume. So let's say that this Tmax epsilon is upper bounded by lambda, which is strictly smaller than the regular isolative entropy, okay, in the limit of large n. Okay, so then let's unpack this. And now the advantage of going to Dmax is that this is a minimum. It's a minimum of smoothings. So okay, so let's unpack this. It means that there is a smoothing that, a smoothing Pn of P tensor n, which is epsilon close, which might be far away because epsilon is not small. And then this Pn is upper bounded by a free probability distribution with some coefficient 2 to the n lambda asymptotically. Okay, good. So now an advantage of assuming all of the axioms, it's kind of that allows me to draw a picture later on, is that Pn and Qn can be assumed to be permutationally symmetric without loss of generality. If they're not, you just permute them. You just apply random permutation, and this will map this free probability distribution into another free probability distribution, because no permutations are free. And so therefore, now the permutation is symmetric, we can, the value on a sequence only depends on the type of the sequence. Okay? So I had a slide on what it means, what the type of a sequence is, but I deleted it because I assume that most of you know. Sorry about that. So the type of a sequence is just its empirical probability distribution, okay? Okay, so like there is a definition there. So the number of, so that its value on a symbol is the number of times the symbol appears in the sequence divided by the total length of the sequence. Okay, so now the picture is like this. So we have this P tensor n, which is an IID probability distribution. So it's concentrated by the law of large numbers around type P. And then the only thing we know is that we have another Pn, which is epsilon close to P tensor n. Okay, so now this Pn is just this sole probability distribution, but I want you to focus on this left part. Since they are a distance epsilon and P tensor n is concentrated around type P, the Pn probability distribution needs to have a weight at least of the order of 1 minus epsilon on this, the set of types close to P. Otherwise, they would be orthogonal, right? If this weight were to disappear, they would be orthogonal. They're not. They're a distance epsilon, which is fixed. It's bounded away from 0. Okay, so we have this little weight, and apart from this, we know nothing. Okay, what do you do? And now the step 3 is this kind of key technique, which I call blurring. So why blurring? Well, blurring because it's what you do to a picture. For example, let's consider this picture of my two co-authors betting whether the Stein's lemma holds or not. And now you might want to blur this one, for example, because it's embarrassing, but also because if you blur it, you don't see anymore who owes $50 to whom.
Still didn't get it.
Yeah, still didn't get. Yeah, that's what I wanted to ask. Yes. Right. So okay. So out of metaphor, what is blurring? So let's say you fix n and m, and you should think of this m parameter as a small fraction of n. Now the blurring map is this operation that we do to, we apply to classical probability distributions over n copies of the alphabet. And it's composed of three operations. The first one is you add m symbols drawn in an IID fashion according to the full support probability distribution Q naught that you find in the first level of the hierarchy by assumption. Second operation is you apply a random permutation, and the third operation you discard m symbols. So you go back to a sequence of length n. And this is a stochastic map, so it's a classical channel, right? So anything you know for quantum channels applies here. And by the axioms, this maps free states to free states because all of these three operations are free. No, the green one by all of the axioms, essentially. Well, three of the axioms, plus convexity. Okay, so, right. So we are in this situation right now. So now we can apply blurring. And now we get a new blurred probability distribution P tilde n on the left-hand side. The inequality is preserved because this is a channel. And on the right-hand side, you get a new free probability distribution, okay, which is obtained by blurring Qn. Nice. So, okay, this is, okay, what have we gained? It's a bit unclear. But now if you look at the picture, it's much clearer. So blurring means exactly that you blur the features of this Pn. And what this does is it makes some weight, the weight on every type class, spill over to nearby type classes, okay? So it's something like this. Right, you add some noise, and the weight kind of spreads out a bit. But the advantage of doing so is so what happens on the right-hand side, we don't care. We care about what happens on the left-hand side. You see, we had some weight of total weight 1 minus epsilon over here, but now because of this blurring, we have spread it out over the whole set of types close to P. Okay, so now this P tilde n kind of covers all types close to P with some weight. There are no holes anymore. And this is really good because it allows us to, up to cutting the tails of P tensor n, considering only the typical sequences, you have this approximate domination. So you can dominate this P prime n, the P tensor n with cutoff tails, with a small exponential multiple of P tilde n. That is really nice. You pay this small price, this delta prime, but this is asymptotically negligible. And okay, so this is the situation. So now we have this P tensor n, which is now eta close, so very close to P prime n, because we just cut off the tails. And this P prime n is dominated by P tilde n. Okay, so now this eta is very small again. Now we can change this with the previous inequality that we had, this domination of P tilde n, and we get a domination of P prime n in terms of a free probability distribution with also coefficient approximately lambda, or 2 to the n lambda. So you can repackage this using the max relative entropy, the smoothed max relative entropy. This is exactly what you get. You get an upper bound on the max relative entropy with eta parameter. Now eta is small. Okay, so you're in this situation now, and now remember what I told you, when eta is small, the quantity on the left-hand side is approximately the regularized relative entropy of entanglement. We can prove this formally with asymptotic continuity, for example, and now we get our contradiction, because you see we have the regularized relative entropy of resource in this case on the left-hand side, and we have lambda, which is strictly smaller than that on the right-hand side. And this gives our contradiction and, in fact, concludes the classical proof. Okay? Yes, there's a question?
Could you describe how the heck did you get rid of the delta prime?
So what do you want to know about delta prime?
Get rid of the last.
Yeah, the delta prime is just a fixed parameter that I'm going to take to 0 after I take the limit in n.
Okay.
Okay, so it's not, of course I'm sweeping a few things under the carpet, under the rug, but it's fine. Okay, so I want to also describe how blurring is applied to the other problem, the quantum, the sum of theorem, but let's do the classical case, because it's very different. It's the same technique, but it's applied in a different way. Okay, so this is the generalized classical sum of theorem. So this is what you would want, right? So you would want, okay, so a family that obeys the usual Brandau-Planck axioms, and then you would want the sum of exponent to be given by the regularized, by the reverse relative entropy, unregularized, because you don't need to regularize it. Unfortunately, this is wrong. So if you put it like this is wrong. So there's a very simple counterexample that we have in the paper. It's kind of very operationally understandable, in which the sum of exponent is 0, but the reverse relative entropy is infinity, so substantial gap. So you need to modify this, and There are many ways to do this, but let's, one way is to include what we call axiom 6. What is this mysterious axiom 6? Axiom 6 is the fact that the regularized relative entropy distance from, well, regularized relative entropy of resource is faithful. Okay, so whenever you take a probability distribution that's not in the first level of the free set, or the free sets, you know, then the regularized relative entropy must be strictly positive. Okay, so, right, so on the one hand, this is satisfied by most sets one encounters in practice. For example, if you look at a quantum version of this, it's satisfied for separable states because, you know, we know that the regularized relative entropy of entanglement is separable. And the other important point is that, okay, so now there are a few rules in information theory. One of the rules is that you should never put an entropy in the axioms. The entropy should always come out of the result, never in the axioms. So this violates this rule. But in fact, you can relax this axiom so as to remove this entropy. So and there is a powerful way of doing that, which is due to Marco Piani, which is to introduce restricted sets of measurements that compatible sets of measurements that kind of in this way you can formulate this axiom in a bit more cumbersome way, but it's also without entropy. So it's just something operation that you can check single letter. Okay, good. So this is what, okay, so now we're going to assume also axiom 6, and it will pop up in the proof. Right, so this is what we have to prove. And again, the easy part is the upper bound, okay? So that's as usual. The achievability is always difficult, the converse is easier. So it's not difficult to see that the smoother Dmax relative entropy is upper bounded by the reverse relative entropy. It's not too difficult to see. And in fact, with a little more work, you can prove something a bit more powerful, namely that if you take the limit epsilon going to 0 of the left-hand side, you get exactly the right-hand side. You know, for both lim inf and lim sup over n. Okay, so this is not too difficult to prove. You need to use asymptotic continuity and well, okay, not even asymptotic continuity of the relative entropy and strong converse to the IID-Stein's lemma. Okay, but the hard part is the achievability. So again, proving that the Dmax, the smoother Dmax doesn't go down. And this is exactly what I want to explain. Okay, so again, by contradiction. So let's say that the smoother max relative entropy goes down asymptotically. Okay, so then for infinitely many values of m, we can again unpack this, and we can find a free probability distribution that's epsilon close to something else. Q prime n is going to be a smoothing of Qn, which is free. And now this Q prime n is upper bounded by, again, 2 to the n lambda, p tensor n. And lambda is smaller than the reverse relative entropy. Okay, so now what do we do with this? We apply this inequality on type classes with type in the free set, in the first level of the free sets hierarchy. Okay, so something like this. You take the union of the type classes. This T and T is the type class with type T. So all the sequences with type T. And now you take the free types. Okay, so sure. I mean, this inequality works element-wise. So you can apply this to any set. This is what you get. Right. So now you use very classic result in probability theory, which is unfortunately also known as son of theorem sometimes. Apologies. Essentially tells you that if you apply, if you compute the weight of any type class according to some IID probability distribution, you essentially get the relative entropy between the type and the probability distribution. Okay, so then you can do this on the right-hand side and up to a poly n factor, which is the number of types. A set of types is polynomial in n. That's also crucial insight from Schizol and Kerner, I guess, or from. And on the right-hand side, you get 2 to the n lambda minus the relative entropy, the reverse relative entropy. Remember that lambda is smaller than the relative entropy, than the reverse relative entropy. So the right-hand side goes to 0. So this implies that Q prime n is essentially concentrated on type classes with with non-free type. Okay. Which means that Qn, which is at most at a distance epsilon from that, must have weight at least 1 minus epsilon on types that are not free. Okay, so Qn is a free probability distribution that has a non-negligible weight on non-free types. This is quite bizarre, right? So it's a free probability distribution. How can it have, in the asymptotic limit, a non-negligible weight on sequences that are not free? This is very strange, right? And in fact, it's absurd. I'm gonna deduce a contradiction from this. And the way you deduce a contradiction is exactly using the blurring lemma. Okay, so let's see how. Let's say that Qn has weight at least 1 minus epsilon on non-free types. Okay, so then, there are polynomially many types, so I can extract one type that has weight 1 minus epsilon divided by poly n. Okay, so up to extracting subsequences, I can say that this type will converge or is approximately given by some probability distribution. And okay, so I'm sweeping a few approximations under the rug, but since the type is non-free for every n, up to including some epsilon, you can also make sure that S is non-free. So the limiting probability distribution of this sequence of types is non-free. Okay, then we are in this situation now. Again, a drawing. We have this type S, which is non-free. Let's also draw this S tensor n probability distribution over types. And then we have this Qn. We don't know anything about Qn. We only know that it has significant weight on some type Tn, which is close to S. Okay, approximately for large n is close to S. Now what we're going to do is, again, we blur everything. And we only care about the left-hand side of the picture, and let's blur everything. So again, this weight that Qn had on the single type, maybe it got, it spills over to nearby type classes. And this, if you repackage everything, this means, again, that the smoothed max relative entropy, not the reverse variant, the standard variant, is upper bounded by this. You can put the blurred Qn on the right-hand side because that's free. And this is at most n times a small quantity. Again, by the same blurring lemma. The blurring lemma essentially tells you that if you have some free probability distribution that has some weight somewhere, you can blur that, and that weight will cover all nearby types. That's essentially what this tells you. And now you can repackage everything, and you will deduce that the regularized relative entropy of this type S, of this probability distribution S, is small, essentially 0. And by axiom 6, this S has to be free. It cannot be non-free because of axiom 6. And this gives you your contradiction and concludes the classical proof of the Sanov result. Okay, so now maybe I want to spend a few words on how to generalize this to quantum. I don't have that much time. Okay, so the generalized quantum Sanov theorem is, again, let's state it only for separable states. Separable states satisfy this axiom 6. That's actually not precisely the axiom we use, but never mind. So for separable states, you have that the Sanov exponent is given by the reverse relative entropy. And it turns out that you can prove this by lifting the classical result. So if you know the classical result, you can do a lifting procedure, which is, when it's possible, it's kind of always nice because you don't work very hard. Here you have to work a little bit. So the key step is to take a large K and a measurement so that the reverse relative entropy measured on K copies is essentially equal to K times the unmeasured relative entropy, reverse relative entropy on one copy. And this is possible by introducing a measure relative entropy, using a minimax theorem, and then pinching. Right? This log poly will have recognized this comes from pinching. Okay, in this way you deduce the quantum from the classical. Unfortunately, this is not possible for this is now Stein setting. I forgot to say. So this is not possible in the Stein setting. In the Stein setting, you really have to work directly at the quantum level, which is what makes the proof long. Okay, so what you do is you prove a quantum blurring lemma, okay, which works morally in the same way. So you have a quantum blurring map, which is, I will try to describe in the next slide, but it works essentially the same. And now what you have is that, okay, so if you have an IID state and a sequence of states that's not asymptotically orthogonal to that IID state, it's a distance epsilon, which is not 1, then I can blur this, I can apply a quantum blurring map, which will preserve separability, to this state rho n so that it asymptotically dominates rho tensor n. And what does it mean, to asymptotically dominate? Well, it means that this operator is approximately negative definite, meaning that the trace of the positive part goes to 0. It's kind of an informal version of the lemma. It's not the exact lemma, but it's basically this. Okay, so the blurring map, constructing the blurring map takes a few steps. Well, so you can start from a simple version, which is exactly the equivalent of the classical one. You can take m to be a small fraction of n, and this is fine. Now, instead of a free full support state, you can say, okay, since we have a fixed reference state rho, why don't we blur by adding copies of rho? That will make the analysis simpler, it turns out. So, up to paying a small price, because this is full rank, this contains rho, essentially. So, okay, so then you can blur with rho. That's also possible. And now you have to prove the statement. In this blurring map, I chose the second version. This turns out to be false for an interesting reason. Okay, so the first step you have to do is to purify everything. Okay, so now we're kind of getting into this bosonic lifting step. That's kind of the core part of the quantum proof. So it pays off to purify everything. Since we have permutational symmetry, we know that there exist permutationally symmetric purifications. Okay, so purifications that live in the fully symmetric subspace. And one is IID because rho tensor n is IID. And I call the purification 0. Purification of rho, I call it 0. Ket 0. Okay, so we are in this situation. We have something that resembles, some state phi n that's not orthogonal to something that's IID. Now, by data processing, you can also you can upper bound this trace of the positive part with the trace of the same thing, but including the purifying systems. Okay, sure. By data processing of the trace of x plus quantity. And now it turns out that this one you can rewrite by projecting the second operator. The second operator is permutationally symmetric, so you can just project it down on the fully symmetric subspace because the other blocks don't contribute. The other sure-while blocks don't contribute because of this positive part. This one only has weight in the fully symmetric subspace. On all the other blocks is 0, so you have 0 minus something. It doesn't contribute to the positive part. Okay, so now the advantage of this is that we are in the fully symmetric subspace. And if you have a sequence of fully symmetric subspaces, you immediately think, okay, I can embed all of them in the bosonic space, in the Fock space. That's exactly what you do. So now we are working in finite dimensions, so CD, but CD is too complicated. Let's take D equals 2. We can actually understand things. Okay, so now there's this embedding of all of the symmetric subspaces into the Fock space of a single mode, as physicists would say. So, essentially a harmonic oscillator. And the embedding works like you embed 0 tensor n into the vacuum, and then all the decay states, the decay state with one excitation into ket 1, and so on and so forth. Okay, so now the key kind of physical point that takes 15 pages to prove, but it's very simple intuitively, is that what's the action of the blurring map asymptotically? Well, every excitation one has a fixed probability delta of ending up in the few systems in the delta fraction of systems we trace away. So if you look at it physically, well, what's the map on a harmonic oscillator that, in which every excitation has a fixed probability of getting dissipated to the environment? Well, a pure loss channel. If you've studied any quantum optics, this is going to be a pure loss channel. And in fact, what you can prove, optical fiber, what you can prove, well, this is the description in terms of field operators, and what you can prove, in fact, is that you can prove the strong convergence, this convergence in the strong topology, that this blurring map, if you blur with ket 0, it converges to this composition of maps in which the first one, this E, is exactly a pure loss channel. This E is a pure loss channel, and this is it's just a very simple map with only one Krauss operator. So that one we kind of don't worry about. And now the problem is moved to the Fock space, and we can solve it in the Fock space. And it turns out that the situation you have is something like this. I'm asking whether, given any fixed state phi, if I apply a pure loss channel, E lambda, and I take this limit in M, I get 0. Trace of the positive part, I get 0. Turns out to be false, because the coherent states are an easy counterexample. Coherent states are mapped to pure states, so other coherent states. And this, if you have two pure states, this is not true, because 0 is not in the support of any other pure state. And okay, so there's a simple fix, which is to randomize the parameter delta over which we take the blurring. And in this way, this is kind of easily proved that the Fock space. Okay, and that is kind of the end of the quantum proof. Let's move on to the summary. Right, so if you want to quantify entanglement testing, you need two asymptotic exponents, which are called Stein exponents and sum of exponents, and we have two results that characterize both of them, the quantum Stein's lemma and the quantum sum of theorem, and they can be applied to quantum resources beyond entanglement. And the important point is that there is one technique that solves both, and this technique is this blurring procedure. And with that, I thank you very much.
Thank you very much. We already have one question.
Thank you for the nice talk. First of all, maybe I didn't understand the blurring correctly, but as far as I understood it, you used it once. But do you have a convergence rate to, like in the classical one, to the uniform distribution in terms of the parameters that you specify? Like, do you know how much you get, how close you get to the uniform one, or in the quantum case?
So we just do blurring with a small parameter. We don't. I don't take the parameter large, so the blurring doesn't. It never converges to. It never gives you the uniform probability distribution or anything. Because I always do blurring with a small parameter. You just need to add a little bit of noise, not too much, because this you cannot afford too much. Just a little bit. Okay. These delta parameters, they always have to be small, because in the end we take them to 0.
Okay, but technically you think one could do that? Like if you don't want to do it with a small one, but actually like...
I think you can, yeah, in the classical case, definitely you can analyze everything. Quantum case, it's much more difficult. Okay. Quantum case, I have no one-shot results. I have only this asymptotic limit. Okay. Because I need to take the limit in the Fock space.
Okay, thank you.
Any other questions? Maybe I have a question. So can you say a bit more about like exactly how the blurring happens? Like what's the noise that's being applied?
So I just add a few, like in the classical setting, I just add a few symbols drawn according to the IID probability distribution, a free one with full rank, with full support that you find in the first level of the hierarchy.
Okay.
So just shuffle in a few symbols drawn at random independently according to this one. That's it. That's all you do.
Okay, but it's IID noise basically.
It's IID noise, okay. Yeah. Hannes?
I mean, maybe I can just...
You can shout, yes.
Maybe I just like talk loudly. I mean, but I don't know. So can I understand this like blurring thing as you establishing kind of like a continuity of this hypothesis testing relative entropy and or max relative entropy in epsilon, and then say, well, asymptotically doesn't really matter what the difference is, and then...
Yeah, I guess that's one way to phrase it. And essentially, you relate different epsilons. So one side of the interval, so epsilon close to 0 to epsilon close to 1.
And do we have any hope of getting like a single-shot version of this?
Yeah, in the classical case, you get a fully single-shot bound from which you can deduce all sorts of things. For example, if you want to say, okay, slightly below the rate, I get asymptotic, exponential convergence of the type 1 error probability, you can do that because you have full one-shot control. In the quantum case, very much not. This is really, I cannot say anything at the one-shot level. It's very embarrassing somehow.
Thanks.
Okay, did we have another questions? Yeah.
So I guess the blurring map is not really unique in a sense.
No,
other
very
maps
much not.
that do the same. So
you can like all sorts of variations. You can add other states. You can do other things.
And I guess a part here is that you use the symmetrization, and this is also part of your axioms in a sense for the proof. So one could hope for a blurring map that does essentially a similar job, but doesn't use permutation invariance.
Yeah. I think you can try and cook it up. Yes.
Okay.
I mean, whether it works at the quantum level, I don't know. But
because I was thinking the other proof for the generalized Stein's lemma is also not relying on a permutation.
Yeah.
So this, okay.
Yes. But I mean, as I said, this implies a little more. So maybe this is not true anymore if you don't use permutation symmetry. I don't know. Yeah. But it's a very good question. Absolutely.
Okay. Thanks.
Okay, we have one question from the online audience.
So So, Shan asked, did you run the analysis on HPC or which platform? I mean, otherwise, how you collect your data and then sort it?
HPC. What is HPC? Collect my data.
I don't know.
No, this is like one of the statements that you include in the papers, like no data was collected during the analysis.
Okay, thank you.
Is there one last question, perhaps? If not, before we go to lunch, well, first of all, let's thank the speaker again.